Hello, students. Good morning. Hello, can you hear me? Hello, students. Good morning. Okay, let us start. The title of the lecture of this morning is the P block elements. The P block elements. Okay, thank you, sir. So the title of the lecture this morning is P block elements. And what are the P block elements? These are those elements in which the last electron enters any of the three block orbitals of the respective shares. When the last electron enters a particular orbital, if it is S, then we say those elements belong to the S block. If it is P, if the last electron enters the P orbital, then we say those elements are in the P block. So P block elements are those elements in which the last electron enters any of the three P orbitals of their respective shares. Okay, since a P subshare has three degenerate orbitals, each of which can accommodate two electrons, then we say that any of them can fall into the 6 groups of the P block elements. Okay, the P block elements include the boron family, the carbon family, the nitrogen family, the oxygen family, the fluorine family, and the neon family. And if you look at the electronic configuration, if you look at the electronic table, the P block elements are those elements from the third group, those that are painted yellow, from the third group to the 8th group in the periodic table. You look at it, they are the ones that are painted yellow. So if the last electron of an element enters the outermost P shell, then we say such an element is a P block element. And they start from group 13 to group 18. If you look at it in the periodic table before you, it is painted yellow. The P block is painted yellow from group 10 for the 13th group and goes to the 18th group. And you must have seen that coal is used in the village to cook. Coal is used in the village to cook food. It is nothing but a P block element. For example, carbon. We also have diamond that is used for making ornaments. They are also made up of carbon, so they all belong to the P block element. Even the aluminium foil made up of aluminium is also made up of the P block elements. They are made up of the P block elements. So the P block elements, they have the general group that is known as the electronic configuration as a general block that is the NS2 NP 1 to 6. It could be NS2 NP1, NS2 NP2, NS2 NP3, NS2 NP4. So the general electronic configuration for the P block element is the NS2N P1 to 6. So the P is the one that is varying from 1 to 6. Now, let us begin to look critically at the characteristics, the distinctive feature, what makes the P-block element to be very peculiar. Now, the difference in all the members of the group is really pronounced when you move from the top to the bottom. There is a transition from the non-metals to the metals. As you move from the top of the table to the bottom, in each of the group, there is a transition from the non-metals to the metalloids. And what characterizes this difference is because of the movement, the difference between the S and the P block, you have the transition element in between. And that has caused a variation in the characteristics of the P block elements. The oxidation state of the P block element is maximum when it is equal to the number of valence electrons, that is, the sum of the S and the P makes the oxidation state of the element in the P block to be maximum. Okay, so the P block element, they exhibit more than one oxidation state. They exhibit more than one oxidation state, and they differ from each other by 2 units due to the innate pair effect. The oxidation state differ from one another in steps of 2 units as a result of the innate pair effects. Now, the first member of the P block elements, they differ from the other elements in 2 major respects. Number 1 is the size, and each and every property depends upon the size. And the second one, the second difference, applies only to the P block element, which arises from the effect of the D block in the valence share of the heavier elements. The lower oxidation state becomes stable as the group is descended. It becomes stable as the group is descended. The P block elements, as expected, is more electronegative than the S block elements. And because of that, they form a stronger covalent bond. As you descend the group, the stability of the covalent bond decreases. As you move from the top of any particular group in the P block element down, the stability of the covalent bond decreases. However, they are more electronegative than the S block elements. So each first element in each group cannot expand its octet. And because it cannot expand its octet, the coordination number for each first row is 4. It's a maximum of 4. Every P block element, they exhibit allotrophy. They exhibit allotrophy. What is allotrophy? Is the existence of different molecular forms of the same element in the same physical state. The existence of different molecular forms or crystalline forms of the same element in the same physical state. For example, you have carbon, and the allotropes of carbon are the diamond and the graphite. For another example is sulfur. Sulfur has rhombic, has monoclinic as example of allotrope. So all the P block elements, they exhibit allotropy. When elements in the same physical state, they exist in different molecular forms. That is what we mean when we say an element is exhibiting allotropy. Now, let us look at the trends in the properties of the P group. The trend in the property of the P block, like I mentioned before, is transiting from the non-metals to the metals. And this transition is not smooth. The reason why it is not smooth, like I mentioned before, between the S and the P block element, there are transition metals. If you look at the periodic table, between the S element and the P block element, there are insertion of transition metals, and that makes the transition of the P block properties not to be as smooth as we have in the S block. Now, I've mentioned that what makes the peculiar features of the p block element to be different from each other is the size, the small size, the high electronegativity, particularly of the first row elements. The second row elements, they have less electronegativity when you compare to the first row elements of the p block. They have less electronegativity. And you know, as you descend the group, the size of the element will begin to increase because of the increase in the shares. In the third row of the p block element, you have a higher electronegativity. Remember, the first one, you have a high electronegativity. The second row, you have a less electronegativity. The third row is now having a higher electronegativity, which is not normal. Okay, so there is a gradual decrease in electronegativity for the last two elements. The first row is higher, the second row is less, the third row is higher, but from the last two rows, we now have a gradual decrease in the electronegativity. However, the last element in the periodic in the row has a much higher electronegativity than it is expected. Because of the lanthanide contraction. So let us look peculiarly, let us explain the properties of the p block element using, first of all, the elements in the group 14. Element in the group 14. Remember, the element in the group 14, we call them the carbon family. And this element in the group 14 include carbon, the silicon, which are metalloid, the germanium, which are metalloid, the tin, which is a metal, the lead, which is a metal. So the only non-metal that is present in the group 14 elements is carbon. Silicon and germanium are metalloids, which are commonly used for semiconductors. If you remember the germanium, then we have metals, which are the tin and the lead. So these are the group 14 elements. And if you look at the table before you, the electronegativity, like I've explained before, the electronegativity of carbon is high, then that of silicon is less, then the one of germanium is higher than silicon, then you now have a gradual decrease from tin to lead. Okay, so the same thing if you look at the oxidation states, they have varying oxidation state 2 and oxidation state 4. So now, this is the table that is explaining the structure and the bonding. So if you look at the structure of carbon, it has a giant molecule and is covalently bonded. And examples of the allotropes is diamond and graphite, as I've mentioned before. We have a giant molecule for the silicon. We have a giant molecule for the germanium. Then we have a metallic structure and a metallic structure also for the tin and the lead. And the bonding in the tin and the lead are metallic bonding, but the bonding in the first three elements are covalent bonding. Okay, so let's look at carbon critically. Like we mentioned before, carbon has very two important allotropy forms, which are the diamond and the graphite, and they exhibit the sp3 hybridization. They exhibit the sp3 hybridization. So the carbon atom is sp3 hybridized, and they are bonded by 4 atoms. If you look at the structure, every atom of carbon is bonded to 4 other carbon atoms. Okay, so, and they have a very high boiling point. Why? Because of the intermolecular and intramolecular bonding between the atoms of carbon. Okay, which is as a result of the covalent bonds. And because of that, they have a very high boiling point. Okay, they are extremely hard. Okay, they are not conductors and they are chemically inert. So carbon and its allotropes are extremely hard. They are non-conductors and they are chemically inert. Okay, so each carbon atom is sp2 hybridized carbon atom. They have layer structures with delocalized electrons. when we say delocalized electron, we are talking about electrons that do not belong to a particular atom, okay, that are evenly distributed. So they have a layer structure with delocalized electrons, and this makes them to be brittle and soft. And the structure of graphite conducts electricity because of the delocalized electrons, and they are brittle and they are soft, okay, because of the layer structure. That makes them to be brittle and soft, and they conduct electricity along the layers. Why? Because of the delocalized electrons. So if you see the structure here, is the structure of graphite, which is an allotrope of carbon. Another member of the group 14 elements, the p block element of the carbon family, is the tin. And we know that tin is a metal, and it has a bit two allotropes, the white tin and the gray tin. Okay, so depending on the level of heating, the white tin can be converted to the gray tin. The white tin is metallic in nature, while the gray tin is not metallic. So if the gray tin is cooled, it will be converted to the white tin. So there's a transition between the white tin, which is metallic, to the gray tin, which is non-metallic. And two of them are the major examples of allotropes of tin. Okay, so let's look at the chlorides of the carbon-14 elements. The carbon-14 element, they form two series of chlorides, the dichlorides with oxidation state 2 and the tetrachloride with the oxidation state 4. So the dichloride, they are written as MsCl2, while the tetrachloride are written as MCl2. MCl4 for the tetrachloride, then for the dichloride, MCl2. The MCl2, they have oxidation state of 2, that is the dichloride, while the MCl4, which is the tetrachloride, there's a bit of oxidation state of 4. Or moving down the group, you will, like we have mentioned before, you will observe that the stability of the oxidation state 4 will begin to decrease. The stability decreases. So there's tendency for a change in oxidation state as you descend the group. Why? Because the stability of this oxidation state will begin to decrease as you go from the top of the group down the group. And so the carbon element, they form the most stable tetrachloride compared to other elements, compared to silicon, to germanium, to tin, and to lead. Okay, carbon forms the most stable tetrachloride. However, the stability of the oxidation state 2 increases as you go down the group. And what that means is that lead will have the most stable dichloride in the group. Why? Because as you go down the group, the oxidation state of +2 increases. Now, all the elements in the group 14 elements in the carbon family, they all form tetrachloride. They form tetrachlorides. However, the tetrachloride of the carbon is more stable. Okay, and the tetrachloride are simple covalent molecules bonded together by covalent bonds. They have a tetrahedral shape and they exist as liquid at room temperature. So the carbon tetrachloride, the silicon tetrachloride, the germanium tetrachloride, and others, they all exist as liquid at room temperature and pressure. So the molecules are not polar, okay, but each element chloride bond is polar due to the difference in electronegativity between the atoms. The molecule as a whole, they are non-polar, but each element and chloride bond, the bonding between the element, between carbon and chlorine, that bond between them is polar, but the entire structure is not polar. Why is the bond between the carbon and the chloride polar? It's because of the difference in electronegativity between the carbon and the chlorine, or between the silicon and the chlorine, or the germanium and the chlorine. So the elements the element, the bonding between the chloride element and any of the elements of the group 14 element is polar because of the difference in electronegativity, but the entire structure as it is non-polar. So let's look at the boiling point. The boiling point decreases from the top of the group, which is carbon, to silicon. Then thereafter, there's a fairly steady increase that is observed. Then the lead tetrachloride decomposes even at room temperature to lead 2 chloride and to chlorine. We've explained before that the transition is not smooth. The reason why it is not smooth is because it is moving from the non-metals to the metalloids to the metals. And so because of that, there is expected to be a not smooth transition as you move from the top of the group to the bottom. All the compounds except carbon tetrachloride are readily hydrolyzed by water. So they undergo reactions with water. The only exception here is the carbon tetrachloride, but every other tetrachloride of other elements are easily hydrolyzed by water. Carbon does not undergo reaction due to its inability to expand its octets. Okay, so this is the mechanism that explains the hydrolysis that took place between the tetrachloride of other elements and water. And if you look at this mechanism, there is a gradual replacement of the chlorine with the hydroxy group of the water. And the byproduct is the hydrogen chloride. So there is a sequential replacement of the hydroxy group in each of the bonding, which will now lead to the formation of the salicylic or the salicylic acid. So that is the mechanism. There is a gradual, a step-by-step replacement of the chlorine in each of the 4 bonds with the hydroxy group, which will now lead to the formation of a salicylic acid and hydrogen chloride as the byproducts. There are 2 major oxides that are formed by group 14 elements. These oxides are the monooxides. With the exception of silicon, it's only silicon that does not form monooxides. But every other element in the group, they form monooxide, and they also form dioxides. So however, the stability of the monooxide, they decreases down the group. The stability of the monooxide decreases down the group, while the monooxide are more basic than the dioxide. The monooxides, they are more basic than the dioxide. And this is expected because of the nature of the transition, like we have measured before, from the non-metals to the metalloids to the metals. So the monobasic are more, the monooxides, they are more basic than the dioxide. So the 2 major oxides that are formed by this group 14 element, they are the monooxide and the dioxide. The only elements that do not form monooxides are the silicon. Every other one, they form monooxide and they form dioxides. So, like I mentioned, all the group 14 elements, they form dioxide. And for example, carbon dioxide exists as gas at room temperature and pressure. We know that we breathe out carbon dioxide. So carbon dioxide is a gas even at room temperature and pressure. And the stability of these dioxides, they decrease down the group. The stability of this dioxide decreases down the group. Okay, even the basicity is also decreasing down the group. As the stability is decreasing, the basicity also is also decreasing from carbon dioxide to lead oxide. So the dioxide of other elements, we've said that carbon dioxide exists as a gas at room temperature. The dioxide of other elements, they exist as crystallized solids with high melting points with giant covalent or giant ionic structures. Okay, so we've said the reason why there is a non-smooth transition is because of the movement from non-metal to metalloids and to metals. And that is why the dioxide of other elements apart from carbon, they are existing as crystalline solids. And this crystalline solid, they have high melting points. Okay, and some of them at the middle point are covalent in nature. They exhibit a giant covalent structure, while those at the bottom, they exhibit a giant ionic structures. So this is a typical structure of the dioxides of the group 14 elements using carbon and CO2 as an example, using silicon dioxide as an example. If you look at the bonding of the carbon, it has a 4 valency, 2 connected to each of the oxygen. Okay, so every silicon atom or carbon atom, they are also connected to other 4 atoms. It could be of the same element or different elements. If you look at the structure here now, you will observe that every silicon is connected to other 4 atoms of oxygen. The same thing with carbon. Carbon is connected to oxygen here using 2 bonds connected to each of the oxygen. So every carbon-14 element, they exhibit 2 major oxidation states, the oxidation state 2 and the oxidation state 4. In this place, we can see that each of the elements, silicon, carbon, they are connected to other atoms using the 4 valency. So let's look at the summary of the properties of the oxide. Number 1, we've said that the oxide, they exist in 2 oxidation states. We have the monooxide, we have the dioxides. And here, we said that the carbon dioxide, CO2, is acidic in nature and is a non-metal oxide. It can dissolve in water to give a weak acidic solution. Like we see in the equation here, carbon dioxide can dissolve in water to give you a weak acidic solution. When CO2 reacts with water, it will give you an hydrogen ion and a carbonic acid ion. Okay, the same thing with silicon dioxide. Silicon dioxide is acidic in nature and it's a non-metal oxide like CO2. The difference here is that the carbon dioxide is that the carbon dioxide can dissolve in water, but the silicon dioxide is insoluble in water. That means it cannot dissolve with water, but it can dissolve in concentrated alkaline. Okay, so this is the basic difference between carbon dioxide and silicon oxide. The carbon dioxide can dissolve in water, but the silicon dioxide cannot dissolve in water. But both of them are acidic in nature, both of them are non-metal oxide. Okay, so since silicon cannot dissolve in water, the another fact here is that it is very soluble in concentrated alkaline. Okay, you can see the reaction there that when silicon dioxide reacts with an alkaline, it will give you the trioxide of silicon and water. So you must be able to note the difference between the properties of silicon and the properties of silicon dioxide and carbon dioxide. Okay, the germanium dioxide is amphoteric in nature. That is, the germanium dioxide has the ability to dissolve, to behave as an acid and to behave as a gas, as a base. So it is amphoteric in nature. It can behave as an acid. It can behave as a base. And so the germanium dioxide dissolves in acid. If you look at the reaction there between the germanium dioxide and hydrochloric acid, it will give you the tetrachloride of germanium and water. So it also has the ability to dissolve in alkaline. And if it dissolves in an alkaline, it will now give you a coordinated compound, okay, of ether hydroxide of the germanium, okay, with an oxidation state of 2. So the germanium dioxide and the tin dioxide, the lead dioxide, all of them are amphoteric in nature. They interact, they can dissolve in an acid, and they can also dissolve in an alkaline. So their reactions are similar to each other. The reaction of germanium dioxide, the reaction of tin dioxide, the reaction of lead dioxide are similar to each other. They dissolve in an acid, they also dissolve in an alkaline. However, the peculiar properties to lead dioxide is that it has the ability to decompose upon heating above 300 degrees Celsius. It has the ability to decompose to lead oxide and oxygen when the temperature of heating is above 300 degrees centigrade. This particular characteristics is peculiar to lead dioxide. Okay, the germanium dioxide, the tin dioxide, they do not decompose. It's only lead above 300 that decompose at above the temperature of 300 degrees Celsius. Now, let's look at the hydrides. The hydrides. All the elements form the tetrahydrides. All the elements, the carbon, the silicon, the germanates, the stannates, the leads, they all form tetrahydrides. Okay, the carbon on forming tetrahydride, we call the tetrahydride alkanes. The tetrahydride of silicon, we call it the salines. The hydrides of germanium, we call it the germanes. The hydride of tin, we call it the stannates. The hydride of lead, we call it the pluban. So these hydrides, they form tetrahydrides. They are actually tetrahydrides in nature, and all of them have their peculiar formula and they have their peculiar names. So all lower hydrides, like the hydrides of carbon or silicon, they are colorless gases. They are colorless gases. So the liquids, they have low boiling points due to their weak intermolecular attraction because of the weak bonding between the hydrogen and the carbon. So when we talk about hydride, we're talking about basically the interaction between the elements and hydrogen. That is what leads to the formation of hydrides. And because of the oxidation states of this element, of the group 14 element, they form tetrahydrides. Okay, and so this tetrahydride is basically a reaction between the element and hydrogen. Carbon and hydrogen will give rise to alkanes. Silicon and hydrogen will give rise to salines. Germanium and hydrogen will give us to germanes, while tin with hydrogen will give us to stannate, while lead with hydrogen interaction will give us to pluban. One thing that we must note here is that the tetrahydride of lead are unstable. Okay, but the dihydride of lead are stable. So the plubane at oxidation state 4 is unstable, while the plubane at oxidation state 2 are stable. Okay, the reactivity of this tetrahydride increases as the group is descended. The reactivity increases as the group is descended. Remember, as we are descending through the group of the element, is moving from non-metal to metalloids to metals. And so it is expected that the reactivity will increase as the group is descending. And I've said that the lower hydrides are colorless gases. And the ones that are higher than the lower hydride, they exist as liquid with low boiling points. Why are they having low boiling points? Because of the weak intermolecular attraction between the bonds of the hydrogen and the elements. Now, let us look at the special characteristics, the special features of carbon. We've said that carbon cannot expand its octet. They cannot expand beyond the valency of the octet. And another peculiar characteristic of carbon is that it has the ability to form a long chain with itself. And this is what is called catenation. So carbon can catenate. When we say carbon or there is a bit catenation, what do we mean? The ability to form chains between the carbon atoms. It is peculiar to carbon. Silicon forms only silicon oxygen chains in the silica, in the silicon dioxide. It forms the chain of silicon oxygen chains, as you can see in the structure before you. But carbon has the ability to exhibit catenation. It can form chains, a very long chains with itself. Also, another special characteristic of carbon is that carbon is the only member of the group that can form pi bonds. Okay, and this explains the formation of the double bonds, the triple bonds that carbon can form with itself or with oxygen or with nitrogen bonds. And so it has the ability to form the pi bonds. You know, in every organic compound, you have the sigma bond, you have the pi bonds, but carbon is the only member of the group 14 element that has the ability to form the pi bonds. And this is the basic reason for the presence of double bonds between the carbon atoms, the presence of double bonds between carbon and oxygen, the presence of double bond between carbon and nitrogen. Another peculiar characteristic of carbon is that carbon forms gaseous oxides. Carbon can form monooxides and carbon can form dioxides. And this monooxide and dioxide of carbon, they exist in gaseous forms. They exist in gaseous form. So they have the ability to interact with other elements. They can interact with oxygen, they can interact with nitrogen, with the halogens, they can form gaseous oxides, and they have the ability to exhibit catenation, and they cannot expand its octet. So these are the peculiar features, the peculiar characteristics of carbon that is peculiar to carbon. Remember that carbon is the only member of the group that forms the pi bonds. Now, let us look at greenhouse effects. Greenhouse effects. Now, we've been talking about climate change, we've been talking about the increase in temperature of the world, and what is actually this issue, the warming effect of CO2. Okay, the warming effect of CO2, there are major agents, there are two major, apart from others, there are two major agents that causes increase in global temperature, that is causing changes in climate change. And these are the carbon dioxide and water vapor on the earth. Okay, so the warming effect, the more of CO2 that you have around, the more of increase in temperature. And this will lead to what is known as greenhouse effect on the earth. So the warming effect of CO2 and water vapor of the earth is simply what is known as greenhouse effect. Okay, this warming effect will lead to increase in temperature of the environment, and it will lead to the warming effects in the environment. And this is what is the totality of this is what we also know as the climate change effects. Now, this occurs when gases in the lower atmosphere, they absorb the infrared radiation from the earth. They absorb infrared radiation from the earth and radiate energy back to the earth. Greenhouse effect is a natural phenomenon. Now, listen to this. Now, we have what is called an ozone layer. You look up the sky, you will see the blue color of the sky. That blue color of the sky is the ozone layer. What does the ozone layer does? It's shielding us. The function of the ozone layer is to shield us from the effects of the sun rays, And so when gases from the earth, like the chlorofluorocarbons, like we are burning papers, we are burning bushes, we are burning trees, and all that. When this smoke goes to the air, they interact with the ozone layer, and it will begin to reduce the thickness of the ozone layer. When the thickness of the ozone layer is reduced, then what happens is that the effect of the radiation of the sun on the earth will be very, very high. And when it is high, the gases in the lower atmosphere on the Earth's surface will absorb these radiations. And when it absorbs this radiation, it will reflect back. The radiation will reflect back. Okay, those that are not absorbed will be reflected back. And when it is reflected back to the Earth, it will now lead to an increase in temperature. The carbon dioxide will form a blanket, okay, on this radiation that is being reflected back. The water vapor will form a blanket on this radiation that is reflected back, and it will now lead to an increase in the temperature of the environment. Now we breathe out oxygen, and we take in oxygen. We breathe out carbon dioxide, and we take in oxygen. The plants takes in this oxygen to manufacture their food, okay, while they release oxygen to us. The plant taking the carbon dioxide, they release the oxygen, then we take in the oxygen and we release the carbon dioxide. And so as we begin to fall the trees, we are reducing the level of oxygen that is coming to us, and we will not allow the plants to take in their carbon dioxide, so we have more of carbon dioxide in the air. By the time we are burning bushes, we are burning refuse and all that, we are releasing more carbon dioxide to the air, to the air. And the increasing level of the carbon dioxide in the atmosphere due to the burning of bushes, due to combustion of fossil fuel, due to deforestation, due to the use of chlorofluorocarbons, all these things will lead to an increase in the level of CO2 in the air. And when there is increase in the level of CO2 in the air, the carbon dioxide in the air, there will be an increase in temperature because the carbon dioxide will form a blanket on the radiation that is being reflected back, and it will lead to an increase in temperature, which will eventually lead to change, which we call the climate effect, the climate change effects. So this is basically what the greenhouse effect is all about. And so by the time we carry out deforestation, we are falling trees, we are combusting, burning bushes, burning refuse, burning fossil fuel, okay, then the use of chlorofluorocarbons and increase in methane content in the earth, all these things increases CO2, which will now lead to an increase in the temperature of the earth, which we call the greenhouse effect. So this has led to melting of ice cap. This has led to flooding of low-lying countries, and all these are the things that we are witnessing across the whole world. You see flooding in Dubai of recent, you see flooding in some part of the United States of recent, we see flooding in some part of Turkey of recent. All this as a result of the climate change effect, the greenhouse. So the accumulation of the greenhouse gas effect will eventually lead to the climate change. The greenhouse gas effect will lead to climate change in the earth. So let's quickly recap. Then if you have any question, you can type it so that we discuss it. So far, we've discussed the P block element. Most of you did not connect on time, so I just want to do a brief summary of what we've learned today. We've talked about the P block element. The P block element, like we mentioned, is a region. The P block is a region in the periodic table that includes all the elements from the 13th group to the 18th group. Okay, and this does not include the helium. So there are 35 P block elements, all from the 13th group to the 18th group, okay, in the periodic table. And if you look at the periodic table, the P block elements are painted as yellow in this periodic table. Okay, so they are a group of elements that have a very wide range of properties. What is peculiar about the P block element is because the last electron of the elements that are existing in the orbital P. When the last block of an element is existing in a particular block, then we say that that element is in that block, whether it is L block or P block. But for the P block, the last electron is entering the P orbital, and so we say it belongs to the P block elements. Why are they called P block elements? Like I've said, the difference between them is because the P orbital, the electrons are entering the P orbital, and there's a transition. The peculiarities here is that there's a transition from non-metal to the metalloid to the metals. And because there's an insertion of the transition metals between the S and the P block, that is what is making the variation in the properties of this element not to have a smooth order. So some of the properties are not having a smooth order. They are not decreasing steadily. They are not increasing steadily. Why? Because of two reasons. Number one is that from the top of the group to the lower part of the group, there's a transition from non-metals to metalloids to metals. So we have, for example, in the P block element, we have the boron family, we have the carbon family, we have the nitrogen family, we have the fluorine family, and we also have the last group of the family, which is the neon family. Now, there are two peculiar properties, like I mentioned before, of the P block elements. The number one is the size of the P block elements. The size of the P block elements, okay, makes the properties to be different from one another. And also the issue of the transition make the properties to be different from each other. The inclusion of the transition elements in between the S and the P block is what is also making the difference. For example, we did a peculiar studies on group 14 elements. The group 14 elements include the carbon, the silicon, the germanium, the tin, and the lead. And if you look at that group carefully, you will notice that carbon is a non-metal. The silicon and the germanium, they are metalloids, while the tin and the lead, they are metals. And these account for the reason for the difference, unsteady difference in the characteristics of the elements. And so we've said that every element in the P block, particularly in the carbon 14 family, they exhibit allotropy. And what do we mean by allotropy? We are talking about elements in the same physical state, but they are existing in different molecular forms. And we said carbon, for example, exhibits allotropy, and the example of that allotropy of allotropes of carbon are the diamond and the graphite. Okay, then we say that that the other example is when we talk about the allotropes of tin. That tin also exists in two allotropes, the white tin and the gray tin. And we said that in this group, 40 elements, they form two basic monoxide. We have the two basic oxide, the monooxide and the dioxides. And we also said that they form the tetraoxide when they react with hydrogen. Okay, and lastly, we also talk about the peculiarity of the carbon elements. We said the carbon element cannot expand its octet. We said the carbon element exhibits catenation. It has the ability to form chains with itself. And we said the carbon element forms two oxides, the monooxide, the carbon monooxide, and the carbon dioxide. And these ones, they exist as gases. Okay, and we also said that the carbon element has the ability to form pi bonds. It's the only group member that has the ability to form pi bonds. And we said because of the presence of carbon dioxide in the atmosphere and water vapor is leading to what is called the warming effect, which we call the greenhouse effect. And so the greenhouse effect is as a result of the absorption of infrared radiation by the gases in the lower atmosphere, okay? And on radiation back to the earth, they form a plaquette, which causes an increase in temperature, a phenomenon which we call the greenhouse gas effect. It's a natural phenomenon, okay? So far today, we've talked about the P block elements. In our next lecture, we are going to be looking at another group, another family of the P block elements, which is the halogens, the fluorine, the chlorine, the bromine, the iodines. And this is where we'll close the curtain for the lecture today. Any question? Please ask if you have any question. You can type it. If you have any question, you let us know. Okay, in the absence of any question, thank you very much. We'll meet on Wednesday as we carry on with the lecture for the week. God bless you. Thank you. All right.